Okay, going back now to section 10.3, relating the linear and angular variables. So this will allow us to go back and forth between the angular variables that we got in the first two sections and our linear variables that we already know from chapter 2. So the short of this is that the linear and angular variables are all related by r, which is the perpendicular distance from the rotation axis. Any of the angular variables, if you multiply them by r, you get the linear equivalent. So for position, we can get our arc length, which is a linear distance, even if it's in a circle, based upon our angular position if we take our angular position theta and multiply by r, that perpendicular distance. A key note here is that the angle theta must be in radians. Radians are our SI unit. So previously, our calculators were often in degrees. Here, you really need to make sure that they're in radians if you're doing these calculations. For the speed, once again, we need our angular variable in radian measure, but we take omega, our angular velocity, multiply by r, and we get our linear speed. So as long as we have omega in radians per second, then this will work out properly to give us our linear speed. And note that here's a figure of it. I apologize, it's a little small. But if we have this egg rotating, the circle traveled by point P you could calculate the arc length of that, S, which would be the total distance around if you made one loop. And that's multiplying r, the radial distance from the rotation axis to point P, that point of interest, and then multiplying it by the angle of how far you rotate around. Maybe it's 2 pi if it's a complete circle, or maybe it's only pi if you only went halfway around. The velocity vector is always going to be tangent to the circle around the rotation axis. So that's a key detail. It's not in the same direction as the angular velocity. So you want it to always be tangential. And one other note as we're talking about things rotating is we can also express the period in radian measure. You can note from some conversions, sorry, I'll stop moving the mouse there, that's equal to 2 pi divided by the angular velocity. And there's some more details that can be done to show that, or you can take the end result and run with it. Similarly, we can look at our tangential acceleration. And once again, radians really matter here. So if you have your angular acceleration in radians per second squared, which are the units of angular acceleration, and multiply it by the radial distance r, then you get the tangential acceleration, which is the acceleration that is tangential to the motion. So down here we have the acceleration shown at point P, and the tangential one is the one that's pointing tangential to that circular path being taken. This is in contrast to the radial acceleration, where the radial acceleration we could write in terms of our angular velocity. If we remember our radial acceleration, this is the one we actually already know. The radial acceleration is that inward acceleration, inward center seeking. Yeah, it's our centripetal acceleration. It's equal to v squared over r. So here we have an a sub r to specify that it's in the radial direction, but you could also call it a sub c, and that'd be just as fine. And you can, using the conversions on the previous page, write this radial acceleration in terms of the angular velocity squared times r, where the angular velocity is in units of radians per second, keeping those units straight. Now this is a really key detail, that the acceleration will always have to have that radial or centripetal component. That's something we have seen, must have that no matter what. If you're moving in a circle or any part of a circle, have to have radial or centripetal acceleration. The tangential acceleration is kind of a bonus one. That one only applies to if the rotation itself is getting faster or slower. So let's try this out. Oh, and if you want the overall acceleration, before I move on, note that because these are at a right angle from each other, you will have to combine them, right? So if you have your tangential, a sub t, and the radial is pointing downward at that angle, but I'm going to actually move it so that's over here. So we can draw it tip to tail to show how they would combine. So this is my radial acceleration, and then my final overall resultant would be from the original tail to the final tip. Sorry, the yellow is a little light. And that would be my net acceleration. So you'd have to think some about vectors and how you can combine them. But because this is a right angle, you can get magnitudes by just using Pythagorean theorem. And that is pretty useful. Okay, so now let's try this out with a checkpoint. So a cockroach rides the rim of a rotating merry-go-round. If the angular speed of the system, merry-go-round plus cockroach, is constant, does the cockroach have radial acceleration, tangential acceleration? If omega is decreasing, does the cockroach have radial acceleration, tangential acceleration? So answer yes or no for all 4 parts of this, and go ahead and write that down before you move on. So hit pause now. Okay, did you hit pause? I really hope you did. You have a last chance to still hit pause. Okay, let's check. So yes, no, yes, yes. In other words, for all the radial accelerations, they have to be yes, because the cockroach is riding in a circle. Circular path must be radial acceleration. But if it's a constant angular speed, there's no tangential acceleration. So that's where part 2 is no. It's only if that angular speed is increasing or decreasing that there is a tangential acceleration. And so that's why for part 4, that is indeed yes. So that is where we will wrap up on section 10.3 relating the linear and angular variables.